Hey everybody. Okay, you should recognize these graphs we talked about last time, right? And said get familiar with their shapes and which function that they go with. Okay, so we're gonna really delve into graphing these on this video. Let's think about though for a minute. Remember when we first started graphing these linear functions and then we realized, oh, every single linear function's graph is a straight line. The only difference is, it might be located in a different place or sloped differently or something, but every linear function's graph makes a straight line. Same thing here. Every quadratic equation, the graph is a parabola. Now, it might be fatter or skinnier or upside down or over here, but it's got this basic parabola shape. Same for all of these. Okay, so what I want to do now, what I want to be able to do is I want to be able to just quickly, like this, just very quickly plot these basic shapes. And we're going to do that with just using a few basic points. So for example, usually we're going to think of points from -2 to +2, and I only have one operation. Now why I'm calling these the basic shapes, notice I don't have a 3x squared plus 2 or anything. It's just x squared. And by the way, I know they're using function notation, but when I'm graphing, I like to change that f of x to a y. I just prefer it. It's obvious then what my x and y's are. And, kind of helps me with what I'm doing. So, let's see. Oh yeah, so our basic points. If I let x be these, I only have one operation to perform to get my y value. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So I can get those just immediately without really having to make a table. Since it's one operation, okay, -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And because I know the corresponding shape, I can fill it in quickly. Same thing here. Think about this. -2 cubed is -8. -1 cubed is -1. 0 cubed, right? Can get those points very quickly. Now, I got a couple of exceptions down here, right? Because if I tried to plug a -2 into a square root, I can't do the square root of -2 or -1. So, but I just recognize that right away. But okay, 0 then. I'm going to start with, notice there's no graph over here where x's are negative. Square root of 0 is 0. Square root of 1 is 1. Oh, I can't really do the square root of 2 either, and and get a numeral I can graph on a graph, or the square root of 3. Oh, but the square root of 4 is 2. So we kind of adjust that. Same thing here. I can't, the cube root of -2 I can't do, but the cube root of -1 is -1. Cube root of 0, cube root of 1. Can't really, cube root of 2 or 3 or 4 can't do, but oh, the cube root of 8, right, is 2. So I can quickly get these points if I know this shape. So we want to work on that. We're going to continue to do that today, so hopefully we'll get well versed at that. All right, but let's see why that we want to do that. We're going to do that to help us graph all of these kinds of functions. We already know how to graph this one, but now we'll be graphing just all of these kinds of functions here, our basic functions, very easily. Okay, so what we're going to use to graph these are something called transformations. Right? Just like when you're graphing a linear equation, really all you need is the slope and the y-intercept, right? The y-intercept kind of slides it up and down your axis, and then the slope tells you how to adjust your points accordingly. So here is our basic function. Again, look how quickly we could get those points. If I had a grid drawn, I would think, okay, absolute, because it's an absolute value, that's my basic operation here. The absolute value of -2 is 2. Absolute value of -1, so I would have a point here. Absolute value of 0 would be 0. The absolute value of 1 would be 1. Absolute value of 2 would be 2. And then because I know the shape that corresponds to absolute value, I could fill that in. Now, notice I drew X's here instead of dots like for connecting my points. That's because this is not really the graph that I'm drawing, right? I want to draw this graph, which they have done for us down here. But let's look at what that means. All that means is every one of these points, this point right here that was on my basic graph just went down 1, 2, 3, 4. Okay, so if I took this point from my basic graph and went down 1, 2, 3, 4, took this point and went down 1, 2, 3, 4, and this one 1, 2, 3, 4, and this one 1, 2, 3, 4. Notice what I have. Oh, because I know it's a V shape and I have enough points to find that V shape, I could draw it in. So that's called translating this, technically vertical translation because it slid down. Anytime you have a number added or subtracted to the end of your basic operation, it's just going to slide your graph up and down the y-axis, right? Just going to slide it up and down. Okay, so let's look at a horizontal translation. The horizontal translation, it comes into effect whenever the number is added or subtracted inside your operation. Your horizontal, anything that's inside the operation, inside the absolute value bars, you know, inside the square, inside the square root, right? Anytime you have anything like that, it affects your x values. If it's outside, like the one we just had, it affects your y's. So when it's outside your operation, it's going to be a vertical translation and slide up and down your y-axis. If it's inside, it's going to be a horizontal translation and slide back and forth across your x-axis. So notice the same deal here. Okay, here's our basic points for our graph. Okay, and every point has just been moved right for 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, etc., etc. 1, 2, 3, 4, and then I could graph that. Yes, you could also make a list of points, but that takes a long time. We should get so comfortable with this, again, that it takes like that long to do these graphs. And sometimes getting a list of points is really tedious because, again, normally we start with like -3, -2, even when we're getting a group of points. If I did that, notice what I'd get for -3 and 2. I'd have these points up here. And I'd either mistakenly draw a straight line, or knowing that it's supposed to be a V shape, might take me forever to find, well, where is that vertex finally at so that I can draw my shape in. So it's very, very tedious. Okay, let's see what we have next. Those are translations, or you can also call them slides, back and forth or up and down. That happens when we add or subtract numbers either to the entire operation or to the x value inside the operation. Notice also this one, even though it's a -4, it slid to the right 4. So anything that's inside the operation is really going to do what appears to be the opposite. We had this -4 over here and it slid our graph down. But anything outside your operation, so out here or out here, is going to affect your y value. Well, if I moved this over with the y value that it's affecting, it would be, and again, just for ease of talking about it, it would be y plus 4. So really they do the same thing. It's just that once we solve for y, we've already moved everything over here and kind of made it have the opposite sign. But inside with the x, it's going to appear to do the opposite. So if this would have been a plus sign, it would have moved left 4 units. Okay, next we have stretching and shrinking. That's what happens when we have a number that's being multiplied to our operation, right? Okay, so here's our basic graph again, and notice they've got those points. They've got those points plotted for us that we would do immediately, that we can get just as quick as just drawing them like this. And then because it's outside the operation, okay, it's going to take the y value only, so the x value would stay the same. Since this y value is 2, I'm going to change the y value to 2 times 2, or 4. Okay, x isn't changing. Since this y value is 1, when I multiply it by 2, it would change to 2. Okay, so this is what we call stretching the graph. That should be obvious when we see the equation that it's stretched because we have a number bigger than 1, right? A number bigger than 1. But the graph, look at the graph, it's actually skinnier than the original equation. And if we look at what happens when we shrink 1, this is an example of shrinking. When the number that you're multiplying by is between 0 and 1, so a fraction, a proper fraction, then we call that shrinking the graph, which makes sense. If we're, taking half of something, we're shrinking it. But look, the actual graph wound up fatter. So sometimes that's confusing to people when they see a graph. They want to say, oh, this has been shrunk. This has been stretched. But no, it's been shrunk. Think about this. If you had a wad of gum and you stretched it vertically, you stretched it, what's going to happen as you pull it? It's going to get skinnier. Or if you had a big wad of gum and you compressed it, you shrunk it, what's going to happen is it's going to get skinnier and flatten out, right? So that's why when we're looking at the graph, it gets fatter when it's shrunk and skinnier when it's stretched. Okay, but the same thing here. Here's my basic value or my basic graph. Okay, it's outside again. It's affecting the y. So because the y is 1, I would take half of 1, and that's why that point winds up right there. Okay. Now, if it's inside, it's doing a horizontal stretching and shrinking. If the number being multiplied is inside and being multiplied by the x, and it does the opposite. So if I had a half in here being multiplied by the x, I would double the x value. Okay, do the opposite when it's inside with the x. The other transformation is a reflection, right? And a reflection makes a mirror image. Okay, so again, and that's what negatives do. If the negative is outside, it's affecting the y value. So I would quickly, now they've switched over to an absolute, to a radical graph. So I would quickly get these points right here, because square root of 0 is 0, square root of 1 is 1, square root of 2, square root of 3, square root of 4 is 2. And I know my shape looks like this. Okay, so then I just look at every y value, and because this y is 2, then I would make the y -2. This y is 1, I'd make the y -1. Negative 0 is still 0, so, and then I know the shape. Okay, again, if it's inside, then it affects the x. So same here. Here's my same points, right? But this time, because it's inside, if I'm looking at x is 1, that would make x -1, and the y is not going to change. So I'd have it here. Here, x is 4. The y is not going to change, but x is going to be -4. Okay, let's practice this. That's our translations. Here's a summary of those. So if you want to copy these down or read over this, right, what I would say the most important thing is, well, it's telling you here, if you have a plus k, you translate it k units up, right? Minus, it goes that many down. If it's inside with a plus, you go to the left. If it's got a minus, you go to the right, so do the opposite. If you're multiplying by a value, right, then it says stretching. Unless it's a fraction, a proper fraction, then it's a shrinking, okay, etc., etc. The negatives inside and outside. So there's just kind of a summary. But what I would add to this, if I were you, what's really important is when you are doing, these are real simple if you're just doing one operation, but if you're doing multiple transformations, we really need to do them in a certain order. So here's everything that you could have combined. And this right here, again, this could be squared or cubed or square root or cube root or absolute value, right? Just doing a generic thing here. The order you need to do these operations in, and sometimes it doesn't matter depending on which ones of these you have, but sometimes if you do them in the wrong order, you're going to get the wrong answer. So I would say always just do them in the same order. Do this first, your horizontal slide, and then this horizontal stretching and shrinking, vertical stretching and shrinking, and last your vertical slide. So I would write that somewhere and keep that in mind, and we'll remind ourselves as we go through this. Okay, so here's some practice. All right, so the first one is an absolute value. So here's what I want to be able to do. Very, very quickly, I want to get my points for just a basic absolute value of x. So if x is -2, the absolute value of x is 2. If x is -1, absolute value is 1. If x is 0, and again, use x's because I don't want to confuse them with the actual points on my graph. Okay, so look how quickly we could graph that. And that was with me talking over it and also explaining. So eventually you should just be able to say, oh, it's absolute value. Boom, 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 boom. Okay, now, let's label them just to remind us the ones that we have. So I'm going to take every x value and move it left, opposite direction when it's inside, 3. So I'll take this and move it over 1, 2, 3. Okay, I'm going to do this a step at a time the first time. 1, 2, 3. So I'll continue 1, 2, 3. 1, 2, 3. 1, 2, 3. So I'll continue to use x's. Just doing it a step at a time. On the others, we're going to do it all at once, but just to see. So if the only thing we had was this absolute value of x plus 3, here's our graph. And it is, notice, slid to the left 3. I would draw it in. Okay, now let's do this step, which is a negative, and it's outside the operation, so it's going to affect the y's. So I'm going to take this, and I'm going to say, oh, my y value is 2, so negative of 2, it would put that down here. Here, for this point, my y value is 1, so it needs to actually be -1. Now, my x's aren't going to change. This one, -0, is still 0. Here's another 1, so I would move to -1. And here's another 2, so I'd move to -2. Now, if I didn't have this +1, this would be my graph. But I do have that +1. So as my last step, I'm going to take every one of these and move it up 1. Now that I've done all my steps, those are actually going to be points on my graph. So I'm going to move each one up 1. And there's the V shape I'm looking for. So you can continue to do them step by step if you want. But on the next ones, I'm going to try to combine it and see if we can just do it in one fell swoop, right? Okay, all right, so let's try it again. I don't know if y'all can hear my husband snoring in the background or not, but I apologize for that. Sorry. Okay. Okay, so now it's a cubic equation, right? So my basic points, if I did -2 cubed, that's -8, okay? And just so it fits on here, these really aren't really good grids. Let's make it go by twos. Okay, so -2, it would be -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. So here's my shape. It comes up like this. I want to tell you something else too. When you're doing a cube, don't go straight across here. The shape of a cube, it has a hump there. And later, when we're getting some more involved with the cubes, we'll find out what that actually means. So when I draw in my cube, make sure that we put a little hump there. Okay, whoops, I got off on where my 1 was. This is 1, and this is 2. Okay, so imagine drawing it in. It's got a little hump. So that's what the cube shape looks like. But we are going to, there's nothing inside with the x, so this would be first step, second step. So we are going to take half of every y value, half of the y value of each of those points, and then move it up 2. So I'm going to start with this. Because my y value is 8, half of -8, half of that's -4, and then if I move it up 2, it winds up right here. Here's my next point. My y value is -1. Half of -1 is -1/2. And if I move it up 2, that's going to be 1.5. Right? Because here's a -1/2. So 1.5. Okay. On this one, my y value is 0, and half of 0 is 0, so it's going to move up 2. On this one, my y value is 1, okay, and half of 1 is 1/2, and then when I move it up 2, right, it's going to be 2.5. This one, my y value is 8, so when I take half of 8, it's 4, and when I move it up 2, it'll be 6. Notice it has that same basic shape, but it's really been shrunk and moved up, right? It's kind of been flattened and shifted up. All right. Let's try the next one. It's a square, so I know its basic shape is a parabola. And I can quickly get those points by saying, okay, -2 squared is 4, -1 squared is 2, 0 squared is 0, -1 squared is not 2, good lordy. Okay, -1 squared is 1, 1 squared is 1, and 2 squared is 4. And there's my basic parabola shape. Now don't make it have a V, it's got a curve there. Okay, so we are going to, here's 1. Now I got a couple of choices here. I can treat this as a 1/2 and then a negative, and then flip it and do it in 2 steps. But if I just multiply my y value by -1/2, it'll do it all at once, right? So I don't have to do it in 2 steps there, even though it is a reflection and a shrinking. It'll do it all at once by multiplying by -1/2. So let's take this point. My y, it's not inside with the x, so it's affecting the y. My y value for this is 4. So -1/2 of 4, half of 4 is 2, and the negative of that would be negative 2. But then, don't forget we got to add 4, right? 1, 2, 3, 4. Okay, this y value is 1. Negative 1/2 times 1 is negative 1/2. But then we add 4. 1, 2, 3, 4. This y value is 0, so negative 1/2 times 0 is still 0. So let's add 4. 1, 2, 3, 4. This y value is 1. Negative 1/2 times 1 is negative 1/2. But then I need to add 4. 1, 2, negative 1/2, sorry. This y value is 1. So negative 1/2 times 1 is negative 1/2. And then I need to add 4. 1, 2, 3, 4. Okay. This y value is 4. So if I multiply 4 by negative 1/2, that's negative 2. But then come up 4. 1, 2, 3, 4. You might also notice on the absolute value and the quadratic functions, they're symmetric, right? So I knew once I got half of it done, I knew where these points were going to fall. Actually, at the end of this, we're going to talk about symmetry, but that's also something we could use in the graphing. And then because it's a parabola, I'm going to fill it in, not making a point there, but a curve. And notice what it is. It's that same parabola shape, but it's upside down, and it's shrunk, so kind of like been mashed, and it's slid up. Okay, I'm going to see if I can just, I forgot about the dots, but still, that's okay. That's fairly quick. Okay. The next one is a radical. So if I try to do square root of negative 2, oh no, there's no negatives under a square root. So I'd start with 0. Square root of 0 is 0. Square root of 1 is 1. Can't do square root of 2, square root of 3. Oh, square root of 4 is 2. So I could easily get those points. All right? All right. Now, same thing. I need to multiply by my y values by 2 and then move it up 1. So since my y value is 0, 0 times 2 is still 0, and then up 1. Okay, here my y value is 1, so 2 times 1 is 2, and then up 1. Here my y value is 2, so 2 times 2 is 4, and then up 1. And then there's my shape. It still has that same basic shape, but it's been stretched, so pulled up, right? And along with slid up. Okay, the last one on this page is still a radical. Oh, I could have left my points there. Oh, no, it's not. It's a cube root. It's a cube root. Okay, so my basic points. Okay, the radicals are the ones I have to kind of adjust my, negative 2 through 2. So I'm thinking, I can't do the cube root of negative 2, 3, or 4, but the cube root of negative 1 is 1. And the cube root of 0 is 0. The cube root of 1 is 1. I can't do the cube root of 2, 3, 4. The next one is 8, right? So the cube root of 8 is 2. I'm just going to put it here. And then there's one over here for negative 8 that's negative 2. Okay, that function goes like this. It's just kind of the opposite of the cubic function and flipped. right? It's the inverse of it. Okay. All right. So I need to be able to get my points. That's the most important, or one of the most important things. And then this first, there's nothing over here. So all we have to do is move every one of these points. Don't forget, if it's inside with the x, it's going to do the opposite. So move every one of these points, right 1 and up 3. So if I move this right 1 and up 1, 2, 3, 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 right 1, let's imagine it's right 1 and up 1, 2, 3. If I go right 1, I'm off my screen. So, and then there's the basic cube root shape. Okay, so that's way easier than trying to plot enough points to get that shape there, and particularly in these, there are points that, you know, we're not going to be able to actually calculate and put on a graph, so very handy. Another reason it's very handy to know these translations is I don't even have to know what the function is to do this. All right, so let's look at these. So it's saying here's some function. Let's find f of x plus 3. So we're going to just add 3, which means move every point up 3. 1, 2, 3. Let's do this one in the oh no, I won't put it. I was going to put them all on at the same time in different colors so we could see the difference, but we won't. Never mind. I think that'd be too cluttered. So up 3. 1, 2, 3. I might want to, there's not an actual point here, but I might want to go 1, 2, 3, just so I know where to draw it. Okay, 1, 2, 3. 1, 2, 3. And then draw in the same shape. If we could draw, we would draw in the same shape. There. Imagine that one's not there. Okay, this, if it's inside with the x, it's going to move along the x-axis and in the opposite direction of what it appears. So I would just move every point left 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And same thing, if we could draw, we would draw that same basic shape in. Sorry guys, no artist, not even close. All right, one more. This one has 2 operations, a horizontal and a vertical slide. So we'll move every point to the right 2, because do the opposite when it's inside with the x, to the right 2 and up 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. And then draw in the same shape, if we can. Okay, so those are our transformations. All together, they're called transformations. Let me know how that goes. Now we're going to talk about symmetry. So think about what it means to be symmetric. You know, it's the same on, it's like the mirror image, you know. Hopefully we're pretty symmetric. If we drew a line right down the middle of our nose, you know, we should look the same on one side as the other. Kind of like the mirror image. And looking in the mirror is the best example of that. So the graph of an equation, okay, so it's graphs we're talking about that are symmetric, of course, is symmetric with respect to the x-axis Okay, in other words, here's the x-axis. So symmetric with respect, we're doing y-axis first. So symmetric with respect to the y-axis if you replace x with negative x. So that would be like our absolute value and our parabolas, right? If you fold it over on the y-axis, they look exactly the same. All you do is replace x with negative x, and if you get the same thing, it's symmetric with respect to the y-axis. So y, you replace x with negative x. Okay, the graph is symmetric with respect to the x-axis. Okay, and notice none of these would be functions if they're symmetric with respect to the x-axis. But to tell if the equation is that way, then you replace y with negative y. And if you get the same thing, it's symmetric with x. Notice, to tell about the y-axis, you replace the x's. To tell about the x-axis, you replace the y's. Okay, to see if it's symmetric with respect to the origin, okay, so an example of that might be our circles. Okay, then if you replace both x and y with negative x and negative y, then we call it symmetric with respect to the origin. Okay, so let's practice that. That's pretty easy. All I'm going to do is just replace and solve these equations, but I just have to remember which one's which. So this one says, see if it's symmetric with respect to the x-axis and the y-axis. So if we're going to test the x-axis first, okay, then I need to replace y with negative y. So I just come over here and literally make that negative y equals x squared plus 4. Okay, now solve it back for y. That means I'm going to multiply or divide through by negative 1. So y equals negative x squared plus 4. Is that the exact same? No, it does not. Sorry, guys. Good grief. Okay. Negative x squared minus 4. Is that the same thing we started with? No. So it's not symmetric with respect to the x-axis. Let's try y-axis. That means let's replace x with negative x. And then simplify and solve for y. So y equals, a negative squared is still x squared. Oh, that is the same thing. This one is symmetric with respect to the y-axis. So it has y-axis symmetry, but no x-axis symmetry. Okay, and by the way, it could have both. So I got to check both. All right, let's go back to this one and let's check x-axis symmetry. So x-axis, you replace the y with negative y. So x squared plus negative y squared. And then simplify it, again, a negative. Okay, it is symmetric with respect to the x-axis. Let's check y by replacing x with negative x. Oh, it is symmetric with both, right? Both x and y symmetry. Okay, let's check this one. And that's all there is to it, right? So for x-axis symmetry, we're going to replace that with a negative y. There's really no simplifying to do. So I already know that's not the same. Let's replace the x with negative x. Multiplying this together gives me negative 2x. And that's not the same. So this is neither. Come on, pen. Neither. Let's check this one. X first, so that means we want to replace the y. And if we simplify that, we get the exact same thing. So it has x-axis symmetry. Let's check for y, which means replace the x. And there's really no simplifying to do. So this one only has x-axis symmetry. Okay? Alrighty. Okay. Oh, now it's asking about symmetric with respect to the origin. That means I need to replace x and y. So negative y equals negative x cubed. Okay, and so negative y equals, because a negative cube still stays a negative. No, not symmetric with respect to the origin. Let's try that. Hey, didn't we just do this one? Okay, x and y. You might already be able to tell what's going to happen with this. It is symmetric with respect to the origin. Notice then, if something is symmetric with respect to the x-axis and the origin, then, x-axis and y-axis, then we know it's symmetric with respect to the origin. Likewise, if something is symmetric with respect to the origin, it's symmetric with respect to the x-axis and y-axis. Okay, so here's some concepts. Okay, a graph is symmetric. Oh, we just said this. With both x and y-axis, it's automatically symmetric with respect to the origin. Okay, a graph symmetric with respect to the origin need not be symmetric with respect to either axis. Axes is plural for axis. And an example of that is our cube function, actually. It's symmetric with respect to the origin, but not the x or y axis, either one. But if it's symmetric to x and y, if it's symmetric to the origin, it's symmetric automatically to x and y. But just because it's symmetric to x and y doesn't mean it's symmetric to the origin. Okay, so of the three types of symmetry, with respect to the x-axis, y-axis, and origin, a graph possessing any two types must also exhibit the third type. Okay, so any two types. So if it's symmetric with respect to x and y, it's also symmetric with respect to origin. Okay, but if it's symmetric with respect to the origin, it doesn't necessarily mean it's symmetric with respect to the others, unless it's also symmetric with respect to one of them, and then it would have to be symmetric with respect to all three. A graph symmetric with respect to the x-axis does not represent a function, and we also said that. Okay, here's just another kind of chart showing that, what x-axis symmetry looks like, y-axis symmetry, and origin. So there's the example of the cube with the origin symmetry that's not symmetric with x or y. And finally, we have even and odd. Now, the symmetries, x-axis, y-axis, and origin, can apply to any equation. As a matter of fact, think about that x-axis symmetry we just said can't be a function. But if you're talking about functions in particular, then we call those symmetries even and odd. And so the only way a function can be symmetric, it can be symmetric to the y-axis, and it can be symmetric to the origin. So it's asking the exact same thing. I'm going to do the exact same thing to find these out. This has a little bit of a different definition, but I'm just going to say, oh, if it's symmetric to the origin, then I don't have to remember something extra, right? And the way I can remember which one is which, right? Hopefully we should be able to remember that, hey, this one that's symmetric with respect to the x-axis is not a function, so that's not one of my even or odd ones. And the odd one is the one that's symmetric with respect to the origin. So that odd helps me remember origin. And so then it must be the other one, the y-axis one, that's even. Okay? So let's try that then. Determine whether these functions are even, odd, or neither. And the first thing I would do is replace these with a y. So when I rewrite it, I'm going to replace it with a y because I'm just going to imagine, oh, I'm asking about y-axis symmetry and origin symmetry, right? It's the same thing, y-axis and origin. So to see if it's symmetric with respect to the y-axis, I'll replace x's with negative x. So 8 negative x to the fourth minus 3 negative x squared. And because these are both even exponents, it gets rid of those negatives. So this one is even. And once I figure out now, it can't be even and odd both, right? It can't be even and odd both. It's either even or it's odd. So that one's even. Let's try this one. So y equals 3 negative x squared plus 5 negative x. Y equals 3x squared minus 5x. That's not the same. So it's not even. Let's see if it's odd. That means replace the x and the y, right? It's the same thing as saying origin symmetry. So the x and the y. So that's negative y equals 3x squared minus 5x. Getting rid of that negative on my y, negative 3x squared plus 5x. Is that the, nope. Nope, this is neither. All right, let's do this one. Okay, so let's try even first. 6 negative x cubed minus 9 times negative x. So y equals, this would be still a negative, so negative 6x cubed plus 9x. Nope. So let's try, that was even, let's try odd. Just going to get rid of all this right quick. So if you're looking at it, you can pause it. All right, so that means replace x and y because it's the same thing as checking for origin symmetry. Okay, so negative y equals 3 negatives. This would stay negative. A negative negative would be positive. Get rid of this negative on the y. Oh, yep, this one's odd. Okay, so practice those transformations and our symmetry, and let me know if you have any questions, and I'll see you next time.